We are constantly hearing about capturing carbon. I mean, it feels like every single week there's a new headline about, a giant vacuum facility sucking CO2 out of the sky.
Right, or some factory putting a state-of-the-art scrubber on its smokestack.
Exactly. And it is virtually always framed as this ultimate finish line. Like, you capture the carbon, you save the world. But nobody ever talks about the massive physical, logistical nightmare of what you actually do with it next.
Yeah, it is a profound blind spot in the public conversation, honestly.
It's as if we've spent all this time figuring out how to bag up the garbage, but we completely forgot to buy a garbage truck.
That is exactly it, because we are talking about millions of tons of invisible gas.
Yeah.
You cannot just, leave it sitting in a pile behind a factory. Moving this material is an engineering and economic puzzle that is arguably just as complex as capturing it in the first place.
And that is the exact mission of our deep dive today. We are exploring the wild economics and the intense physical engineering required to transport all this captured carbon across continents for you.
It is a massive undertaking.
It really is. We are going to look at why it might actually be cheaper to load CO2 onto a ship and sail it across the entire European continent than it is to just pipe it to the town next door, which sounds completely counterintuitive.
Oh, completely backward. But the math is solid.
Yeah, the underlying physics and math tell a fascinating story. And, okay, let's unpack this. We are pulling all of this from a highly detailed paper. The title is a bit of a mouthful, but it sets the stage perfectly. It's called Techno-Economic Design of Integrated Infrastructure for CO2 Transportation to Sequestration and Utilization Sites.
Yes, and this study is remarkable because it refuses to look at just one piece of the puzzle. It examines the entire board.
Right.
But to understand the infrastructure, the pipelines, the ships, the trains, we actually have to start at the end. If you are moving millions of tons of CO2, well, the final destination dictates every single engineering decision made along the route.
That makes total sense. You don't lay down highway pavement until you know what city you're actually driving to. And this study breaks those destinations down into three main pathways, or the three C's. I want to make sure I have these right. So the first is CCU, or carbon capture and utilization.
Yes.
And this seems to be the scenario where we don't throw the carbon away at all. We treat it as like a raw ingredient and recycle it into something new, like e-fuels.
That is correct. In the context of this study, they are specifically looking at turning that captured CO2 into green e-methanol.
Okay, e-methanol.
Right, which is a highly versatile synthetic fuel. It can be used to power cargo ships or heavy industry without relying on newly extracted fossil fuels. You are essentially taking carbon that is already above ground and keeping it in a closed loop.
Which brings us to the second pathway, right? CCS, or carbon capture and sequestration.
Yes, exactly.
This is for the hard-to-abate industries. Like, the study uses cement manufacturing as an example, because cement naturally releases CO2 as part of its chemical baking process, regardless of what energy source you actually use.
Right, it's unavoidable.
So CCS is grabbing that industrial emission and permanently burying it deep underground.
Yes, and that permanent burial is really what distinguishes it from the third pathway, which is CDR, or carbon dioxide removal.
Okay.
So CDR operates on the exact same mechanical principle as CCS. You capture the gas and put it underground, but the source of the carbon is fundamentally different. CDR deals strictly with biogenic CO2.
Meaning carbon that originated from plant life, right? Like trees or agricultural waste.
Exactly that. Because a tree spends its entire life pulling CO2 out of the atmosphere. If you burn that tree or process it at a pulp and paper mill and then capture that specific emission and bury it, you are actively removing carbon from the natural cycle.
Wow.
We're creating net negative emissions.
So CCS just stops us from adding more pollution to the atmosphere, but CDR actually dials the Earth's thermostat down by reversing the flow.
That's a great way to put it.
So we have utilization to recycle it, and then we have these two types of carbon storage.
I am going to have to stop you right there.
Oh, did I mess that up?
Well, it is a very common habit, and you see it constantly in the media. But we really need to correct the vocabulary here. It is not carbon storage.
Okay.
The correct term, which this study deliberately uses, is carbon sequestration.
Wait, is there really a functional difference? Because they kind of sound like interchangeable terms for just, putting something in a box.
There is a massive difference both technically and psychologically.
Yeah.
The word storage implies a temporary state.
Oh, right.
Yeah, if you put your furniture in storage, the implication is that you intend to open the unit and take it out later. But for CCS and CDR, we are talking about permanent CO2 waste disposal.
Huh.
We are taking this carbon, injecting it deep into the Earth's crust, and we never ever want it to come back up.
That makes a lot of sense.
Calling it storage gives a completely false impression of the goal. It is permanent sequestration.
I really appreciate that distinction. It shifts the whole mindset. So to visualize this for you listening, CCU, the utilization, is like recycling plastic water bottle into a park bench, right? It gets a second life. CCS, capturing the cement emissions, is like throwing your trash into a highly secure, high-tech landfill so it doesn't pollute the neighborhood.
Exactly.
And then CDR, the biogenic removal, is like actively taking a boat out, pulling old trash out of the ocean, and burying it so the ocean is fundamentally cleaner than when you started.
That is a perfect framework. So now that we understand our three possible destinations, recycling it via utilization or disposing of it permanently via those two sequestration methods, we have to actually figure out how to move it from the source.
Right. And this is where the study grounds everything in a really tangible, real-world case study. They focus on Southeast Finland.
They do.
They identify two massive emitters located a mere 6 kilometers apart. We have a cement plant providing our industrial emissions for CCS and a pulp and paper mill providing the biogenic emissions for CDR.
And combined, they are capturing 2.24 million tons of CO2 every single year.
Which is just a crazy number.
To put 2.24 million tons into perspective, imagine a cube of pure CO2 gas at normal atmospheric pressure. That cube would be over 1 kilometer wide, 1 kilometer long, and 1 kilometer high.
Wow.
And that is just 1 year's worth of emissions from 2 facilities in one small corner of Finland.
The scale's just staggering. But there was a detail regarding how we handle this gas that I had to pause and reread because it seemed almost excessive.
Oh, the purity requirement.
Yes. Before you can put the CO2 into a pipeline to move it away from these plants, the study notes it must be 99.9% pure. And furthermore, the water content has to be stripped down to below 50 parts per million.
It has to be incredibly dry.
But why does it need to be so clean? I mean, for a waste product that is literally just being shoved into a metal pipe for disposal, why bone dry? I initially assumed a little moisture wouldn't hurt anything.
Well, it is a very natural assumption to treat it like wastewater. But pressurized CO2 mixed with even tiny amounts of water is a recipe for catastrophic engineering failure.
Really?
Oh, yeah. You create two immediate severe problems. The first is chemical, which is carbonic acid. When H2O meets CO2 under intense pressure, it forms an acid that will literally eat through the carbon steel of a pipeline from the inside out. You get this devastating rapid corrosion.
Oh, wow. So the pipeline would essentially just dissolve itself.
Yes, it would. And the second problem is physical. It's called hydrate formation. Under the immense pressure required to move gas through a pipe, water and CO2 molecules can actually bond together to form solid ice-like crystals called hydrates.
Oh, so you're forming physical obstructions in the pipe.
Exactly. Imagine slushy ice plugs spontaneously forming inside your pipeline.
That sounds terrible.
It is. They restrict the flow, they cause violent pressure spikes, and they can completely rupture the entire system. So getting the water content below 50 parts per million is not about being pristine or eco-friendly. It is purely about preventing the pipeline from tearing itself apart.
That makes total sense now. We have to strip it down to pure bone-dry CO2. So now we have this purified gas and we need to move it. This study evaluates a few methods, right? Pipelines, shipping, electric trucks, and electric trains. I imagine pipelines are the standard workhorse here.
Well, pipelines are excellent for continuous point-to-point movement over short distances. But you cannot simply blow millions of tons of gas through a pipe like air through a straw.
Right.
The volume is just too large. You have to manipulate the physics of the gas. You have to compress it into what engineers call a dense subcooled liquid phase.
I assume that requires an immense amount of pressure.
A phenomenal amount.
Yeah.
The study models the pipelines running at a massive 15 megapascals of pressure.
What does that mean in normal terms?
To visualize that, 15 megapascals is roughly 150 times normal atmospheric pressure.
Whoa. So you are squeezing the gas so aggressively that the molecules have no choice but to behave like a liquid.
Precisely. It becomes incredibly dense, and that allows you to force a massive volume of CO2 through a relatively narrow pipe. It also requires less energy to push a dense fluid along than it does to push a highly expansive gas.
Okay, that makes sense.
However, achieving 150 times atmospheric pressure requires enormous compressor stations spaced along the route, and they draw massive amounts of electricity just to keep the pressure up.
Which leads me to ships. Because if you want to put the CO2 onto a marine vessel, I mean, I have to imagine you can't realistically keep a tank at 150 times atmospheric pressure. The walls of the tank would have to be incredibly thick, solid steel.
Right.
The ship would be too heavy to float economically.
You've hit on the exact conundrum the maritime industry faces. Building a ship with steel tanks thick enough to withstand 15 megapascals would be economically ruinous. The vessel would carry more steel than actual cargo.
So what do they do?
Well, what's fascinating here is the engineers employ a brilliant workaround, which we can call the 7-bar trick.
The 7-bar trick. Okay, how do they manipulate the physics on the water?
Instead of using extreme brute force pressure to force the CO2 into a liquid state, they use extreme cold, supplemented by just a moderate amount of pressure. So they liquefy the CO2 at 7 bar, which is only about 7 times atmospheric pressure.
Oh, that's way lower.
Exactly. It's something very easily managed by standard commercial tanks. But to keep it liquid at that low pressure, they had to drop the temperature all the way down to around minus 50 degrees Celsius.
I see. So on land, they squeeze it into a liquid. On the ocean, they freeze it into a liquid.
That is the fundamental difference. Now, cooling millions of tons of gas to minus 50 Celsius requires heavy-duty refrigeration equipment on the ship, which obviously burns fuel and costs money.
Right.
But the trade-off is remarkably favorable. Because the internal pressure is only 7 bar, the walls of the ship's tanks can be dramatically thinner and lighter.
Oh, and a lighter ship requires less fuel to sail.
Yes, and it has far more buoyancy available to carry actual cargo, rather than just dead weight. This study notes that optimizing for this lower pressure state can reduce overall shipping costs by up to 30%. It completely upends the economics of moving carbon.
A 30% reduction just by swapping pressure for refrigeration. That is phenomenal engineering. Okay, so we have our pristine CO2. It's either heavily squeezed in a pipe or deeply frozen on a ship. Now we need to figure out the final disposal. Let's look at the two sequestration destinations, our permanent waste disposal sites that the study analyzes, because it is a direct showdown between Norway and Iceland.
Yes, our CCS and CDR permanent routes. Let's examine the contenders. First, we have Iceland. And Iceland offers a fascinating method, which is onshore mineralization in basaltic rock.
This is where they inject the gas and it reacts with the volcanic rock, right?
Yes, exactly. The CO2 dissolves into water and is pumped deep underground into specific basalt formations. And over a surprisingly short time frame, chemical reactions occur that literally precipitate the carbon out as solid carbonate minerals.
It turns to solid stone.
It does. It is incredibly secure because once it's a rock, it cannot leak back into the atmosphere. Moreover, the raw injection cost is remarkably cheap. The study puts it between 7.9 and 10.2 euros per ton.
Turning a greenhouse gas into solid stone for around 10 euros a ton, that just sounds unbeatable. So what is Norway offering in response?
Well, Norway offers offshore geological sequestration. Instead of volcanic rock, you are pumping the liquefied CO2 deep under the seabed into vast saline aquifers.
What's a saline aquifer?
It's essentially a giant layer of porous sandstone filled with ancient salty water. Now, the infrastructure required for offshore platforms and deep-sea wells is much more complex, meaning the injection costs are significantly higher. The study prices Norway between 15 and 16.8 euros per ton.
Wow, okay. So Norway is almost double the price at the high end, and it stays a fluid rather than turning to stone.
Yeah.
Looking at those raw numbers, I naturally deduce that Iceland wins in a landslide. Cheaper disposal fee, safer end state, it just seems obvious.
It does seem obvious until you calculate the logistics. And this is exactly why the researchers modeled the entire integrated system, not just the injection sites. When you factor in the total cost of the operation, the cheapest option for permanent sequestration in this study is actually Norway.
Wait, really?
Yes, specifically loading the CO2 onto an electric train in southeast Finland, taking it to a port, and shipping it to Norway.
That is wild. How does Norway end up being cheaper overall if the disposal fee at the site is double the cost of Iceland?
Because in the waste disposal business, transport distance is the supreme dictator of economics.
Oh, I see.
It simply does not matter how cheap the landfill in Iceland is. If you have to charter a specialized ship to sail thousands of extra kilometers through the North Atlantic to get there, Norway is geographically much closer to our emitters in Finland.
Right.
So the massive savings on shipping fuel, the drastically shorter transit times, the reduced capital tied up in the journey, all of those accumulated transport savings completely wipe out Norway's higher injection costs.
It really emphasizes that the logistics of the garbage truck matter infinitely more than the gate fee at the landfill.
Exactly.
But, that raises a question about the safety of Norway's method. You mentioned injecting this pressurized liquid beneath the seabed. If I'm permanently disposing of millions of tons of CO2, I want to know it is staying down there.
It is a critical concern, absolutely. Offshore geological sequestration in places like the North Sea is currently treated as a highly viable standard option. The caprock above these saline formations has held natural gas in place for millions of years.
Okay, so it's proven to hold gas.
Yes, however, the study is transparent that it isn't without risk. There are documented real-world instances where the injected CO2 plume migrated in ways geologists did not perfectly predict.
Oh, really?
Yeah, and they have also recorded unusual pressure buildups within the formations during injection.
So we can't just pump it down there, pack up the rig, and forget about it.
Not at all. While the risk of a catastrophic leak back to the surface is considered very low, it demands rigorous, continuous seismic monitoring to ensure the integrity of the storage site.
Right.
It is safe, but it requires active long-term management. This is quite different from Iceland, where, once it mineralizes into stone, the risk profile essentially drops to zero.
All right, so for waste disposal, sequestration, geographical distance is the undisputed king. The shortest trip wins, even if you pay a premium at the destination. But what if we aren't throwing the CO2 away? What if we are recycling it via CCU? Because this is where the study takes a massive counterintuitive turn.
Yes, let's shift gears from waste disposal to synthetic fuel production. In this scenario, we take that same 2.24 million tons of CO2 from Finland, but instead of burying it, we want to synthesize it into green e-methanol.
Okay.
The study models two primary options here. Option A is keeping it domestic. We build a pipeline to move the CO2 to the Finnish city of Oulu, and we use local domestic wind power to run the e-methanol factory.
Well, that feels logical. If short distance wins for waste, keeping the processing local via a pipeline should be the winner for utilization too.
Right.
What is the alternative?
Option B is radical. We put the CO2 on a ship and we sail it thousands of kilometers away entirely across the European continent down to the coast of Spain.
Wow.
And we use Spanish solar power to synthesize the e-methanol.
Okay, here's where it gets really interesting. You just laid out the math proving that a short trip to Norway beats a long trip to Iceland because transport distance dictates the cost.
Right.
But for utilization, this study proves it is actually economically superior to load this CO2 onto ships and send it all the way to Spain than it is to pipe it a short distance within Finland's own borders. How does that make any logical sense?
It all comes down to the underlying mechanics of how you manufacture e-fuels. Making green e-methanol is not just a simple matter of mixing CO2 and water in a vat.
I assume not.
The crucial ingredient you need is e-hydrogen. And to get green hydrogen, you have to split water molecules into hydrogen and oxygen using a process called electrolysis.
And breaking water molecules apart takes a lot of energy.
It requires a truly staggering amount of renewable electricity. It is incredibly energy intensive.
Okay.
Therefore, if we look at the broader map of Europe, we have to consider natural resources. Spain possesses arguably the best solar irradiation conditions on the entire continent.
Right, lots of sun.
Exactly. The cost to generate the massive, continuous amounts of solar electricity required for electrolysis in Spain is significantly lower than generating the equivalent amount of wind power up in Finland.
So electricity is the true bottleneck of the entire operation.
Exactly. Because you need such vast quantities of electricity for the synthesis process. If we connect this to the bigger picture, the cost of powering that factory absolutely dwarfs the transportation costs.
It dwarfs the transport costs so significantly that it actually pays for a specialized refrigerated boat ride across the entire continent.
Yes, the savings you generate on the Spanish electricity bill are larger than the entire cost of chartering the ships to bring the carbon there.
That is wild. It's like, imagine you run a premium coffee shop in Italy, but instead of buying locally roasted coffee beans, you charter a ship to bring raw, unroasted coffee beans all the way from South America to Italy simply because the electricity to run your espresso machine happens to be a few cents cheaper in Rome.
That's a great way to put it.
I mean, in any normal logistical mindset, it sounds crazy, but when the electricity is the main expense, the spreadsheet dictates the logistics.
The spreadsheet absolutely rules here. When you are synthesizing e-fuels, the energy costs are the undeniable center of gravity for the entire operation. It dictates where the industry will physically plant its flag. Carbon will travel to wherever the power is cheapest.
This has been an incredibly revealing journey through the invisible infrastructure of climate tech. Let's bring this all together for you listening. We started with 2 factories in Finland capturing millions of tons of CO2. So what are the fundamental takeaways?
Right.
First, the sheer engineering required to move this gas is intense. You have to achieve 99.9% purity just to stop the pipelines from dissolving from the inside out, and the maritime industry relies on that brilliant 7-bar freezing trick to make shipping economically viable without sinking the boat with thick steel.
Exactly.
Second, if you are strictly focused on waste disposal permanent CCS or CDR sequestration geographical distance, is your master.
Yeah.
The cheapest option is a hybrid rail-to-ship route to the closest viable geological formation, which in this case is Norway, even though the actual burial fees are higher than Iceland's miraculous stone-turning process.
Right. Distance is key there.
But third, and perhaps most surprisingly, if you are recycling that carbon into e-fuels via CCU, electricity prices become your master. Shipping is surprisingly flexible and affordable to the point where it makes total economic sense to export your captured CO2 across a continent just to chase cheaper solar power.
And that specific realization leads to a profound shift in how we view this gas. For decades, carbon dioxide has been treated strictly as a localized waste problem.
Right, just pollution.
Exactly. It is a pollutant that you try to get rid of as quietly and cheaply as possible. But the transport economics modeled here prove that CO2 is rapidly transitioning into a highly mobile, globally traded commodity.
It completely reframes the narrative. And again, this comprehensive breakdown is drawn from the detailed modeling in the paper, techno-economic design of integrated infrastructure for CO2 transportation, to sequestration and utilization sites.
And I want to leave you with a final thought to mull over, building directly on that idea of CO2 as a commodity. We just explored how it makes perfect economic sense for Finland to ship its carbon to Spain to chase cheap solar power.
Right.
As the global demand for green e-fuels skyrockets over the next decade and the maritime infrastructure to ship CO2 safely becomes standardized, are we going to see a geopolitical paradigm shift? Will we soon witness a world where countries blessed with massive solar or wind resources actually compete to import other nations' carbon emissions?
Wow.
Instead of paying exorbitant fees to hide it underground, will captured carbon become the new crude oil that nations actively fight over to feed their synthetic fuel industries?
Nations aggressively competing to import other people's pollution. What an absolutely wild concept to consider. It brings us right back to where we started. We focus so much of our attention on the glamour and the triumph of capturing the carbon, we completely forget that the real revolution is in how we move it and who is willing to pay for it. Thanks for joining us on this deep dive.